So it means we can have discussions. So please do chip in with questions, comments, thoughts. This is your time to really pick this man's very, very, very large brain. So I'm going to hand over to you, James. Thank you very much.
Thank you for the introduction. Okay, so I read a book, and so mainly I'm going to talk about the book. I obviously wanted some people to come to the talk, so I gave it the title Artificial Intelligence in the Mobile World, and I promised to do some mobile world stuff, and also there is a Tagg hack I did in the summer of last year that has a long piece about what you need to think about in terms of building an application for real human beings, and that's sort of quite useful to sort of go through. So I'm going to I'm going to try and answer 3 questions. So why is AI so important in mobile? How close is AI to beating a human being? And is it really going to happen at all? Is it feasible? And I have to admit that I'm a bit of an AI Luddite, okay? So there are people who think that AI is just going to trounce mankind and people who don't. I won't give away the plot, no spoilers on the book, but you know, that I should warn you that that's my view. Right, message from our sponsors. I'm CTO of Truephone. If you travel internationally, you end up with a pile of SIMs like this. We give you one SIM, one bill, one voicemail, multiple numbers on that one SIM. So it feels like a local service worldwide. It can switch identities from being an English SIM to a French SIM to a German SIM to an American SIM in under 90 seconds, so it's very good if you wanted to drive a car or a vehicle or do machine to machine. So it's very cool technology. There's no sort of tromboning or home routing of all the data, so the data drops locally, so you get great quality. And it's flat tariff in 66 countries, all of Europe, all of North America, tons of the world. So you can start traveling and roaming around the world on business and not worry about your cost of data and voice and all that sort of stuff. So that's the end of the message from the sponsors. So back to the book. I did actually put it up, and if you go to my listing on iTunes, you find that I'm... Oh, I must take my glass out of the way of the video. You find that I'm kind of in good company. Unfortunately, if you reference their books, you don't get the same list the other way around. It's a one-way algorithm. So the first question is, why is AI so important in mobile? And I think what you have to face is the fact that when you're stationary, you are using tools. It's tool use, right? It's like a hammer or a pair of pliers or some sort of thing. So when we organise this event, we use sort of things like Eventbrite and so on. We went to Facebook, we dragged and dropped friends into boxes, let them go. We moved things, we kind of arranged things and so on. Now, it turns out, and that's very tool use. There's no essential difference between using a computer like that as a tool and when I do plumbing at home. It's a little bit cleaner, it's a little bit sort of, I can sit down while I do it, but it's just plain tool use. When you go mobile, it's quite difficult to use tools, right? Those intellectual tools we use where we kind of organise information, we no longer have the physical real estate to sort of put things here and put things there and compare things. And we're under stress, right? We've got short time. So where are we with AI today? So these are the poster children for AI. So obviously, chess computer has beaten the top grandmaster who ever lived. This is Aaron. Aaron is a computer and composed, whatever you want to call it, that painting. Emily Howell. Have you heard of Emily Howell? Download the CD. Tell me whether it's a computer or not. Right? So is it music? I'll play it a little bit later, and you can tell me what you think of it. And of course, Watson. So IBM's Watson, which beat the top 2 contestants ever of Jeopardy, the one with the highest score and the one with, or the most money, and the one with the most consecutive wins. So it beat both of them. So at the moment, you can see there's quite a slew of artificial intelligence that's out there, and we've got some big projects in the world. So in Europe, we've got a $500 million or euro project going on called the Human Connectome Project, which is like the human genome. And the idea is to be able to map the human brain completely, like the human genome, and know all of the cross connections of all of your neurons. And then, of course, the question is, if you have done that, have you copied a human? So there's a project in America, it's actually a not-for-profit foundation, where some person has donated $100 million as a prize for the first person who can upload a complete human brain into a computer. So there's a lot of kind of sophisticated stuff going on.
What stage is that at, that project?
They are at the very foothills, and they're giving away small amounts of money to people who are making progress towards that goal. And as you can imagine, if you're a fabulously wealthy oligarch or inventor or whatever, right, you might actually want to give a bit of money to that from time to time, just in case, when you get to the end of your life, you'd like to be preserved. So I think they have quite a lot of money that comes in over the transom quite regularly to keep them being able to fund out a little bit of sort of money on the outside. So, it's a strange project. I did stand up at a conference and point out that according to Rice's theorem, you couldn't actually prove that you had cloned a human being unless human beings run on Java. But they didn't quite like my theory. We'll do Rice's theorem properly in a moment. So what we're going to do is do the famous and infamous Moore's law, but do it properly. So we all know Moore's law, approximate doubling of computing power every 18 months. So the question really is, when is a computer going to overtake us? When it's going to be more intelligent than us? There's a few estimates around, and certainly my estimate, if we're classical, and we'll go on to ask what classical means, but if we're basically a computer, in the normal sense of the word, we're just like your IBM PC, but just a bit better and, obviously a bit squishy and made of blood and protein and so on, then my estimate is that we'll hit the parity point in about 2053. Ray Kurzweil, his estimate is about 2047. So I think, broadly speaking, people agree on when we'll hit the parity point. And of course that's why AI has suddenly become so phenomenal in the press, because we're looking at a time when, within the lifetime of many human beings on the planet, maybe even most, if you think that our life expectancies are going up rapidly, we're going to see AIs, and AIs are going to have the same number of transistors or gates as the human brain. So that's quite an interesting prospect. There is, however, a question as to whether the brain is a classical computer. There's a group, a chap called Travis Craddock, in America, is now at Nova in Florida, and he asked the question, scientists believe that there was no quantum mechanical effect that could possibly happen in hot, wet, noisy environments like brains and plants and things like that. And then a group discovered that photosynthesis is in fact a quantum effect. And so in plants, there's quantum coupling between the photosynthesis elements in plants that gives them their efficiency. So what Travis did is he looked at our neurons, and he looked for a set of proteins that are connected to each other, are organised next to each other with the same pattern, right? In the same pattern as chlorophyll, i.e. that they could be doing some sort of quantum effect. And he found some, and this is his analysis that came out probably 3 months ago and hasn't yet been written up by a journalist. However, I have done an article which I'm hoping to put into probably New Scientist about it. And then the other question was, well, of course, photosynthesis relies on light. So where does the light come from, right, in your skull? And so he did a little bit more research and pointed out that mitochondria, which are the power plant in your entire body, actually give out high-energy ultraviolet photons when they excrete them as a byproduct of generating electricity, generating power in the brain. So he said, well, look, there's a source of light, and there's things that are oriented in a way that could be quantum mechanical. That's as far as he's got, right? But there's some debate about that. So if we look at the mobile question, the CEO of ARM got up in 2012 and he said, essentially, Moore's law is irrelevant in mobile because we're not trying to optimize chips for speed, we're trying to optimize chips for power and other things. So mobile runs a little bit behind, and we'll see why in a few seconds. So I'm just going to talk about desktop chips here, and we'll see why. And of course, so let's squidge our Intel map down in the bottom left-hand corner, and let's sort of see what happens. Well, the big problem is that as we move out, and we need to get to somewhere around 2053 to see what's happening, power goes up in an Intel environment dramatically. Somewhere, we might be very, very lucky and only get to 300 watts, but we might easily get to 10 kilowatts with a current sort of rate of increase in power use. And so, if you're trying to optimize for power, which you have to in a mobile environment, you're probably power constrained. Now, of course, the nice thing about human brain is we do manage to pack an enormous amount of power into a relatively small computing engine. So that there is some hope for engineers. If you want to look at sort of what happens as you really kind of push it, then this is where we're kind of going. So if we're a classical brain, then we need to get up into the sort of 10 terabyte or 10 teragate to 100 teragate level in order to make a computer with that sort of power. If we're quantum, we need to go up another about 5 to 6 orders of magnitude to get it, and that will take us to 2080. But even if we're quantum, right, we're looking at parity in 2080. So again, in some people's lifetime, I'll tell you how I come to that if you want later. But of course, the limitation is that we would be at 10 kilowatts if we got there. So this is a linear question, right? And humans do something that computers don't appear to do yet. We are quite creative, and we appear to exhibit free will, right? So we choose to come to events like this. We choose what we say. We create tables and chairs out of cardboard. These are quite wacky and creative things. Creativity is something that wasn't really recognized a couple of thousand years. In Greek times, people didn't think that people invented or created. But today, somewhere like the Talent Garden, this is designed for creativity. We're here to create. And so what I'm going to do is talk a little bit about creativity. So it's a monkey moonshot problem. You know the monkey in the moonshot? President Monkey announces he's going to go to the moon, and the monkey starts kind of working how to go to the moon, and the monkey announces to the president that he's climbed the nearby tree and is well on his way towards the moon. And you go, it's a non-linear problem, right? So if the monkey is climbing a linear problem, the question is there something that you've got to do that's non-linear between the top of your mountain and the moon? So it's a class problem. Is there a different class of things? And I'm going to argue that creativity is a different class of thing. And this is sort of Lucas Penrose's argument. So Roger Penrose, who wrote The Emperor's New Mind, Lucas, who did the Minds and Machines, and argues that we're not. It's also, what's the other one? I can't remember. You see, I'm a human being, so I'm highly fallible, right? Okay, so this is the bit where we get into some mathematics, okay? So if you're all ready, take a swig of your alcohol, have a kind of bit of tapas. I'm just going to have a quick drink.
What's that, amino acids?
This is, yeah, and I need every bit of sugar I can get. The brain runs on sugar, remember, pure sugar. So you take it in and you immediately burn it. It's quite efficient in that respect. No messing around. Okay, so a chap called David Hilbert at the turn of the century announced a series of problems, and one of the problems, and there are 21 of them, and Hilbert's 10th problem was the one about Diophantine equations. And he asked, essentially, could you make a machine, some sort of method like long multiplication, that could solve any mathematical problem? and he specifically posed the Diophantine problems. And it's that problem, which is called the Einschuldigungsproblem problem, that Alan Turing solved in 1936 and is the subject of the imitation game. Right now, they never actually say Einschuldigungsproblem problem in the movie. They say that problem which I can't even pronounce. But that's the thing he did, and that's the thing he really should be famous for, even though he did undoubtedly shorten the World War II by a couple of years, which I guess we all have a lot to thank. And the way that Turing solved the halting problem, well, to solve the halting problem, he had to invent the computer. So he invented the entire computer, and then he came up with this thought experiment and said, well, if I have a computer and I make a thing called halt, right, which is just a function, and then I pipe that, the output of halt. I say, well, if it goes into an infinite loop, or if it loops, going into an infinite loop, otherwise make an output, and then if I feed that back into the input of this, right, it causes a paradox. So it's a paradoxical construction. So what he therefore said is, therefore halt can't exist. There can be no way of making a procedure that will say if some other procedure will finish. So why is that interesting? Well, Pierre de Fermat, who's read Fermat's Last Theorem and all the books and so on, he came up with this idea, which is x squared plus y squared equals z squared, which is simply a 3, 4, 5 triangle, right? And he said, although there are 13 solutions in the square, the 2, so n equals 2, there are no solutions for any other dimension above it. So there's no, the square on the hypotenuse is equal to the sum of the square of the other two sides, there are 13 solutions, but there is no, the cube on the hypotenuse is equal to the sum of the cubes on the other side. There's no hypercube solution or hypercube solution or whatever. And he said he'd proved it, and we don't know whether he'd prove it. Now, an interesting thing, of course, is if you can, this is just something that you could iterate through. You could just try all these, right? So if you could try all these, you could put them into halt, and you could say, try Fermat's last theorem, right, and tell me if it halts. If it halts, then I'll know that Fermat's last theorem is true, else I won't, right? So I could just do this. So what Turing had proven was that since there's no halting problem, there's no halting solution, you can't just throw anything at a computer and have it automatically solved, right? And that's sort of a piece of maths that most of us know from university, and we all dismiss because it's sort of, all Turing said is there's no single one algorithm that can solve everything, right? And that means there's no single one algorithm that could, for example, solve Fermat's last theorem. There's no arbitrary sort of super algorithm that could just do everything. The question, though, is there some clever way around that limitation? Right? Is there some sort of way that you can solve just Fermat's last theorem? Because Turing has said you can't solve everything, right? You can't take some arbitrary thing and put it into an algorithm. Could you kind of get around this? So a bunch of mathematicians worked on this question over many years, and the question was, is a Diophantine equation is something that has whole number solutions solvable by a machine? And eventually, a chap called Matievich managed to prove that it's not solvable. So an arbitrary Diophantine equation is not solvable. So that narrows Turing down and says, particular type of equation, right, that's not solvable either. Just the generality is not solvable, but that specific class is not solvable. Right? Then a few years later, these guys proved that, now the annoying thing about Fermat's last theorem is it's not a Diophantine equation because the n's are variables. So it's called an exponential Diophantine equation. And as soon as you get into maths, you find that changing a single digit in an equation changes the whole nature of the whole field of mathematics. I phoned up one of the top mathematicians on this subject in the world, who's a guy from Aachen, and I said, I'm very interested in this thing, can you explain it to me? And he said, he's written a book about it, and he said, no, I didn't write that chapter. You will have to speak to this other guy. So he wasn't, a single digit change. It was a different mathematician, a different part of the world needs to do it. But anyway, these guys proved that after many years that an exponential Diophantine equation can be rewritten as a Diophantine equation. Now we're in maths land, okay? So he's proven that there is no solution to a Diophantine equation. These guys then prove Fermat's last theorem is Diophantine. That means there is no algorithm which will find a solution, which will tell you whether Fermat's last theorem is solvable or not, and indeed can solve it, right? There's no algorithm that can do it. And then, in 1995, Andrew Wiles came up with a proof. So you've got a situation where you've got no algorithm that can find a solution, and then a human being does it. And that's, to me, the Wiles paradox. How did he do it? That's a simple paradox. Right? Something that is forbidden to be done by a computer has been done, therefore he can't be a computer. And that's my talk.
What? Whoa.
Okay?
Again.
Now,
Define a computer.
now there are some standard objections to my argument, and so there are some backup slides in a moment when you start picking holes in the argument. But that's the essential thing, that humans demonstrably do something that a computer has been proven not to be able to do. Right? So I think that human intelligence is a different class of intelligence than computer intelligence.
How did the chap prove?
Lots of coffee. Intuition.
And you put this in
Mathematical
the
intuition.
same bucket as creativity then, in a sense.
Yes. So there's then a question of, so mathematical creativity you can do these sorts of proofs with, because I can lay out a piece of maths, I can lay out a proof that no algorithm could solve that piece of maths. Then I can find a mathematician who's proven it, and go, aha, got it.
But doesn't that mean you set out the wrong rules to the computer in terms of the algorithm?
Well, it doesn't matter what the rules are, there is no algorithm and no set of rules that could do it.
How does the mathematician then prove it?
It's a one-way problem, right? It's a one-way function. I cannot get from no knowledge to knowledge, right? That's a creative process. Once I've got through the creative process and I've got some knowledge, I can run it through a theorem checker and prove it's correct, right? But I can't do it in the other direction. So it's a one-way problem. I can prove it. I don't discover anything that's like, well, I've discovered something, it's mystically true, I believe it's true. There's no faith involved. It's everything you prove is always then analysable and demonstrable. You might, for example, with the four-colour conjecture problem, have to get a computer to help you because there are so many varieties of map. There's 2,500 varieties of map, so you have to have a computer check your proof because you just can't be, well, it can't be bothered. It would take 1,000 years of mathematicians or something to go through all the proofs mechanically. So you get a computer to help you. But it's a one-way problem.
So we shouldn't be worried about the singularity?
Yeah, so I'm an anti-singularity guy. I think that although computers will get powerful and infinitely powerful, they're traversing the wrong infinity, right? They're going across the countable infinity, and in order to be creative, you need to traverse the continuum, which is the non-countable infinity. So, and that's Turing's original proof. Turing's original proof is a diagonal proof, where he shows that although computer programs are countable, finding solutions to problems is not countable. It's an uncountable problem, and therefore you can't simply iterate through it.
So are there like tens of thousands of developers wasting their time?
No, you can apply. That's human programmers have job security, right? For a given problem, you need to apply intuition to it to make a mechanical solution to it. Once you've got a mechanical solution to it, you have a mechanical solution to however big that problem was. Some problems are quite big, so you work out how to do multiplication. You're done for multiplication, division, addition, a whole class of problems. If you solve Fermat's last theorem, it doesn't help you with its next door neighbour problem, which is the four-colour conjecture, or the Poincaré conjecture, or the Riemann hypothesis, or any of those things. I mean, they're just a different problem, and solving one doesn't really help you solve another at all.
In deep learning, that's just for solving simpler problems?
You've got to give the computer enough hint about the problem space to get over the non-computability of the problem. Once you've got over that and you've given it enough insight, it can go and flash out the whole domain, right, automatically. But you've got to give it enough insight to know what to do.
So you could argue that we're actually building up that insight.
Yes, absolutely.
There's petabytes and petabytes of data.
Yeah, we humans are solving non-computable problems, which we are teaching machines then how to solve the whole sphere of them. But that doesn't mean to say that they can then jump across and do another one. So we can do creative bits and free will, and they can do fleshing out the problem and making it general and doing it way faster than we can.
On that way faster bit, so previous prior to this little lesson tonight, I kind of did believe in this singularity. I'm now, I don't understand some of the maths that you talked about, but I was almost excited by there's this point, you know, you said 2053, I had 2045 in my head, but that's just based on naive predictions.
What?
Of the machines becoming more intelligent than man, and then realising we're the inefficiency.
Yes.
Which is
well, that's Wozniak, isn't it? And originally Shannon, who said, you know, one day computers will treat us like we treat dogs. You know, that we'll just be their pet. And as you say, once you look at human beings, if you're more intelligent than we are, we do a lot. I mean, we damage the planet. We're kind of complete nutcases. We kill each other randomly for no reason from time to time. We don't seem to be programmable. Why can't we just kind of, sort of, you know, upload pianist to human and they can just run around being a pianist? We actually have to train them for 25 years, you know. So that we're quite annoying in many respects as a pet. Probably interesting.
Inefficient is the word, probably.
Yeah, but how many human pets would an artificial intelligent computer want to keep?
It does not compute.
A few 100,000 maybe. It's quite interesting to watch us, you know, organise a city.
We may be in.
Do you really want 8 billion of us?
Already.
You know.
Is this the Matrix?
No, it's a Skynet.
I would like to make sure if I really understand your point. So just to double check. So you're saying basically computers will never able to solve problems like we humans do because they are not have the ability to have creative thinking.
Yes.
Is that
they are a classical computer or a quantum computer is Turing limited, right?
Okay.
It can't solve problems using an algorithm, and we can see, for example, Fermat's last theorem. You can't discover the solution to that problem with an algorithm.
But is there not a chance that there will be a way that we can learn creativity?
Or simulate it, at least.
Okay, so that's the clever machines objection.
Yeah.
Right? So the clever machines objection is, I've heard about this amazing system at MIT, and it uses genetic algorithms, and it learns spontaneously, and my response is, what does it run on? And you go, oh, some supercomputer they've got. So it's an algorithm, right? It's just a clever algorithm, but at the end of the day, it's called algorithm brackets clever underscore clever, you know, open brackets, close brackets, semicolon, and you press return and you run it. And all the cleverness is just an algorithm. And we've just proven that no algorithm can solve that problem. So no algorithm can find another algorithm that would solve that problem. Otherwise, that's an algorithm that can solve that problem, right? Now, there's one major objection, right, that is difficult to defeat, okay? And that one is the that one is the deterministic algorithm, Daniel Dennett. Right? So Daniel Dennett says, you think you're living, you think you have your free will, you think you live, you make decisions, you're deluded, get over it, right? The universe is entirely deterministic, it's a deterministic computer, it simply proceeds from one place to the next, right the way through, right? That's it. So any ideas that you chose to come here, that the traffic, it's all sort of set. But you've got to realise that the presence of non-computable solutions presents a really strong boundary condition for that, right? So a non-computable result in a universe that is deterministic must have existed at the Big Bang, right? That piece of information must have existed, and it must have made its way right the way through the entire algorithmic evolution of the entire universe to the moment at which the dots flew off the dot matrix printer to print Andrew Wiles' proof. Every last thing. And so that means that there would have to be a very large amount of information right at the Big Bang that's pre-programmed into the universe. But if that's the case, then Daniel Dennett can say, well, no, it was always going to happen. There's nothing to explain, James, because he was always going to solve the problem because he was pre-programmed to solve the problem. The universe is a pre-programmed thing. So that's the biggest objection. Of course, the problem then is there's a packet of non-computable information stuffed in the universe at the point of the Big Bang. Where did that come from? Because there's no machine that could have created it. Right? So there's another thing to explain that's equally hard. So I think that means that Dennett is wrong, that his explanation doesn't work. Because there's an equally hard, all Dennett says is, actually the universe all appeared here, and we live in, it's like pressing the DVD. You put the DVD in here, you press play, the universe plays out and we see it. But I want to know, how was the DVD created in the first place? That seems to me to be the actual place the universe exists. We're watching the replay. So we could be watching the replay, right? I don't think we're watching the replay, I think this is the real thing. But it would leave an equally complex problem to solve right back there.
Do you get hate mail?
No, I have a few interesting groupies. Yes. No, actually, it's not true. I have had one piece of hate mail.
Right.
Yes, and I've had 2 cease and desists as well on the book. So yes, and of course here I can insert academic shield.
Yeah.
Right? So I can say whatever I like. But in the book's not protected by academic shield, so I don't have that privilege.
So you don't see any evolutionary jumps, in the way that happens in nature?
Yes, I think we have intuition. I think that there's a non-computable process where we jump ahead.
What about it happening in the machine world? I don't
It's an algorithm.
I don't get too close to any matrixy type conversation, but we start to talk about quantum computers, we talk about nanobots, you talk about whatever it might
Some
be.
extraordinary things are going to happen, and there's some extraordinary. We're going to wake up at a Mobile World Congress one day, and some extraordinary thing is going to have happened. But I'm arguing that what we're not going to have is something that comes and sort of wakes up one morning and decides it's going to have a blue period, right? Those big steps. Because we had, Aaron, way back at the beginning, is quite capable of knocking out thousands of these, right? They all look a bit the same, right? So what you're seeing there is, when I'm saying that a computer can flesh out something, you give it enough rules to create interesting compositions, it can knock out thousands of these. But what it won't do is suddenly wake up one morning and give you Cézanne or Pissarro or any other great artist. Or suddenly wake up one morning and go, oh, I'm not going to bloody paint, I'm going to compose today, right? Which it doesn't have that freedom of will or that creativity. That's the jump in between.
So we will never be perfect, but maybe we will get near enough.
Get near enough. There are pieces of music, right, which have been automatically composed, Bach in particular, where more people think that the piece composed by the computer is better than the piece composed by Bach. So it's possible, and it's one particular piece of music that's used, it's possible to get quite good if you give it enough rules of doing a particular thing quite well. But it's not going to wake up one more. An enormous amount of information was plugged into that thing, so it could essentially copy the genre of Bach. I mean, Bach came up with it himself.
What if we make computers our experience or experience we have as humans accessible? Maybe that will have an impact on their creativity as well. No?
It depends. The problem is it's still an algorithm, right? So what you've done, it's the Turing oracle problem. What you can show it a piece of creativity, right? You can show it a random number, for example. That will give it the ability to generate and use random numbers, but it won't give it the ability to solve Fermat's last theorem. So just arbitrarily giving some piece of information doesn't take that.
So basically, we're behaving the way we behave, and we think the way we think, because we've got feelings, and maybe feelings cause the intuition. So, for example, I won't catch a hot cup of coffee because I know I will get burned, and I have felt how a hot cup of coffee feels like. So, if we can transfer all that feeling to the machine, maybe it will start learning how to feel. Maybe it will start learning the intuition and the creativity, and maybe starting evolving.
Okay, so I've told you how you can't do something. I haven't told you how you could do something.
Exactly.
So, so certainly someone like, so there are a few proposals for super Turing machines around. So Harvard Siegelman has put forward the fact that since we use real numbers, an analog computer in our brain, that could be more powerful than a Turing machine. Roger Penrose and Stuart Hameroff have proposed that we have quantum gravity computers in our heads, so they're both quantum and quantum gravitational, which is something that would be more powerful than a Turing machine. So there are some proposals out there for super Turing machines. Now remember, as soon as someone talks about hypercomputing, they're in the same area as perpetual motion machines, right? Where a lot of people think that that's breaking the laws of physics and so on. So what I'm really just showing quite hard in this presentation is there's a problem with the laws of physics. In fact, there's a problem with computational theory, which is that we see things done in our universe that cannot be explained by